Hello, UMTYMPers. This video is on section 12.6, conjugate roots in Descartes' rule of signs. We're going to start this little bit of class, a little bit of video here with you doing a problem. I want you to solve this equation here. Pause the video, solve the equation. Okay, welcome back. Those are the roots to that equation. Oh, we should say x equals, huh? If we want to be smart. X equals 1 plus or minus 2i. What do you notice about those two roots? If we were in class, you could just tell me, but we're not in class, so I don't know. Here's what you notice about those two roots. They're complex conjugates. So meaning the two roots are 1 plus 2i and 1 minus 2i. So it's a complex number, but the signs, the only difference between the two complex numbers is the sign on the complex part of the number is, or the imaginary part of the number, rather, are opposites. This suggests a theorem, which is true in general, called the conjugate roots theorem. For any polynomial with real coefficients, if a plus bi, the complex number a plus bi, where b is not 0, is a root of the equation f of x equals 0, then we know a minus bi is also a root of f of x equals 0. So what this says is that the complex roots of a polynomial with real coefficients always come in complex conjugate pairs. This theorem is useful because if you have one complex root, you automatically get the other one. You get the other one for free. You know what it is. To prove this theorem, we need a few lemmas. So the first lemma, lemma 1 here, is this tells us if I take the conjugate of two complex numbers, if I take the conjugate of two different complex numbers and multiply them, I get the same result as if I multiply them first and then take the conjugate. That's what that bar on top means. So I'm going to let z1 be the complex number a plus bi right here. And then z2 is going to be the complex number c plus di. A, b, c, and d are all real numbers. So then to prove it, we just multiply it out. So I take the conjugate of both numbers first. So I get a minus bi times c minus di. Multiply it all out. I squared equals -1. And then I get this guy here. And then I take the other side and multiply the two complex numbers and then do the conjugate. So multiply the two complex numbers, multiply it all out, and then do the conjugate, and I get the same thing. I dropped some conjugate signs here, though. That should be there, and that should be there, and that should equal AC minus BD minus, because we take the conjugate, BC plus ADI. And then we've shown what we wanted to do. I can take the conjugates first and then multiply, or I can multiply first and take the conjugate. Get the same thing. Next lemma says that I can take the conjugate of a complex number and then do the exponent, or I can do the exponent first and then do the complex conjugate. Get the same thing. So from the last lemma, I know that I can square something first and then do the conjugate, or I can conjugate it first and then square it by the first one. Then we do induction on M, but you haven't learned induction yet. That's next week. So we're just going to take that to be true. The last one, I want you to try on your own. No, I lied. This isn't the last one. This is one after this. Try on your own. So if R is some real number, you want to show that the conjugate of R is equal to R itself. So if R is in the real numbers, that means R equals A plus BI, but B is equal to 0. A is a real number. So go ahead and pause the video and try to reason through why the conjugate of a real number is a real number, the same real number. Welcome back. Last lemma. We want to show taking the conjugate of a complex number and adding it to the conjugate of a different complex number. It's the same thing as if I add them first and then do the conjugate. Same thing. Pause the video and try to work it out. The procedure's the same as the first one we did. Work on the left-hand side, get to some endpoint. Work on the right-hand side, get to a different endpoint. They should be the same. So pause the video and give it a shot. Welcome back. I hope that went okay for you. Now that we have lemmas 1 through 4, we can prove the conjugate roots theorem. Wait, what was the conjugate roots theorem again? I forgot. That was too long ago. Okay, conjugate roots theorem says if a plus bi is a root of the polynomial f with real coefficients, then a minus bi is root 2. Okay, if I have one complex root, I get the other one for free. So first thing, I'm going to assume that z is a root of f. And then I want to see what I get when I stick the conjugate of z into the function f. And if I get 0, then I'm good. We've proved the conjugate roots theorem. So I take the function f, I plug in the conjugate of z, and that's what I get, that line there. And then we know that we can exponentiate and then conjugate, or we can conjugate and then exponentiate. So instead of conjugating and then exponentiating, like on the first line, I can switch the order of those two things in the second line. And I know the coefficients, the next line here, the coefficients of this polynomial f are all real numbers, and I know the conjugate of a real number is the same as the real number. It doesn't change anything. So I can conjugate all the coefficients ai, and it's still the same polynomial. And I know that I can multiply two numbers and then conjugate, or I can conjugate first and then multiply them. And that's what we've done here in the next line. And then the last one says I can sum everything before or after I conjugate. And that's one of the lemmas that you proved. And this last line here, is the conjugate of f evaluated at z. That's what that is. And we know that f of z is 0 because z is a root of the polynomial f. And what we figured out here is that if I plug the conjugate of z into the polynomial f, I get 0. That means the conjugate of z is also a root of f. So we've proved the conjugate roots theorem. Good? Good, good. I'm glad. You watch it again if that was too much. Just watch it again. Not a big deal. Next problem. Here's a polynomial. I give you a root here. R1 is 6 minus 5i. And I want you to find the other roots of the polynomial. Pause the video. Find the other roots. All right, welcome back. So the other root that I get from the conjugate roots theorem is 6 plus 5i. You just get automatically. You got a complex root, you get the other one for free. I know that if I multiply, we did this in a different video, if I multiply the 3 roots of the polynomial, that I get the constant term, or a negative of the constant term, which is 61 in this case. Then I know 2 of the roots already, 6 plus 5i and 6 minus 5i, times the third root that I'm looking for, and I get minus 61. Do a bunch of algebra, and I get that the third root is negative 1. So my 3 roots are 6 plus 5i, 6 minus 5i, and negative 1. That's nice. That's lovely. The conjugate roots theorem says that for all polynomials with real coefficients, all the non-real roots appear in conjugate pairs. Do irrational roots always occur in conjugate pairs? It's a question. Pause the video, think about it. Either prove that irrational roots always occur in conjugate pairs, or find a polynomial that has a conjugate root or that has an irrational root that doesn't appear in a conjugate pair. Pause the video, prove it, or find a counterexample. Welcome back. Here is a counterexample that irrational roots always occur in conjugate pairs. There's a polynomial, x minus root 2. It has all real coefficients. It's got an irrational root. Its irrational root is root 2. If we wanted it to appear, if it was going to appear in conjugate pairs, negative root 2 would also be a root of this equation, but it's not. So there's a counterexample. Irrational roots don't always occur in conjugate pairs. But we do have this theorem. If my polynomial only has rational coefficients, not real coefficients, so if it's a whole number, a fraction, an integer, or a fraction, positive or negative fractions, if the number a plus b root c is a root of the polynomial f, then I know that its conjugate is also a root. So my polynomial has rational coefficients, not real coefficients, rational coefficients. If a plus b root c is a root, then I know that that conjugate is also a root. What does that mean in your own words? Pause it. Go tell a parent or a sibling what this theorem means in your own words. Go for it. I triple double dog dare you. Pause the video, go tell someone what that theorem means. Okay, welcome back. How is this useful? It's useful the same way the other one's useful. If I have one root that looks like that, I know another one automatically. Just change the sign in the middle there. The proof of this, exercise 45 in your book, walks you through step by step through the proof. Check it out if you have time. It's pretty cool, but I'm not going to go through it here. We have one more tool for finding roots that we're going to go over in this section. Descartes' rule of signs. René Descartes is famous for saying cogito ergo sum, which is I think therefore I am in Latin. He's also famous for the Cartesian coordinate plane. You've probably heard of him before. Maybe when you learned Descartes' rule of signs last semester. Did you learn it last semester? I don't know. Anyway, here's Descartes' rule of signs. If f is a polynomial with real coefficients, and we're thinking about the equation f equals 0, then the number of positive roots is either equal to the number of changes in sign of the function f, or is less than that by an even integer. So if you have 3 sign changes, you're either going to have 3 or 1 positive roots. And then for the negative roots, it's the same kind of thing, but you got to plug negative x into the function. Proof. We're not doing it. It's too long. Here's a problem. We got this polynomial. I want you to use Descartes' rule of signs to state the possible number of positive and negative real roots. So pause the video, give that problem a shot. Okay, welcome back. Descartes' rule of signs tells us that there are 2 or 0 positive real roots. So I have the first term is positive, second term is negative, so there's 1 sign change. Second term is negative, there's another sign, that's not a sign change, so 1 sign change. And then I go from negative to positive, so that's 2 sign changes. I have 2 positive roots, and then I go down by 2, so 0 positive. And you can't have a negative number of roots, so that's silly. And then if I stick negative x into that function, I'll find that there is 1 sign change. And then the non-real roots are whatever's left. The fundamental theorem of algebra tells us that there's either got to be 2 or 0 non-real roots. So to sum up this section and the previous few sections, actually, I want you, this will be fun, try this. What tools do we know so far that we can use to find the roots of polynomial equations? I want you to go on this YouTube video and comment one tool that you have to find a root of a polynomial equation. Let's see how many we get in there. That'll be cool. Okay, good job, guys. I know these videos are hard. You're doing a good job. See you in the next one.